All right. Yeah, so let's continue from yesterday. So yeah, so yesterday I misspoke. So I look at the video and I think sometimes I was thinking of something and then I say another thing. So when I try to say about the value of money is supposed to be subjective, yeah, not objective. So maybe that's why I confused you yesterday. Um, yeah, so yesterday we discussed about the meaning of probability in the sense that there's something that we want to describe or predict or quantify in the real world, that we lump a lot of things together and call it uncertainty. On the other hand, we have a mathematical theory of probability. And last time I said that, okay, the mathematical theory of probability is something that everyone agrees on, at least today. I mean, in the past, there were some debate, but in the end, we realized that everything has to obey some kind of axiom that is equivalent to the Kolmogorov axioms. I mean, you can choose other sets of axioms, but in the end, what we agree to reasonably call probability would still obey Kolmogorov axiom. And then I said that, well, not everyone agree what uncertainty is, and maybe a better way to say that would be that not everyone would agree about whether what kind of uncertainty that probability can describe. And then I present two views, the objective and subjective school of probability. But let's say first what I mean by let's I guess review what I mean by objective and subjective. So this is would be facts, like some outcome of an event, or yeah, or outcome of events, truth value of a proposition. For example, if I say that, okay, if I have a red apple and then say, oh, the apple is red, then that is a fact. And I guess our intuition would say that, oh, that fact is like a property of the object that we're talking about. Like the red color is a property of the apple. So some example we discussed yesterday, like the probability of sunrise. We would be hard pressed to say that the chance of sunrise is a property of the sun, because we know more than that, right? That we have a solar system and everything has a consistent like periodic property. So we are pretty sure if like there's nothing that knocked the sun or knocked the earth off the solar system, we're pretty sure that tomorrow we'll still see sunrise. But from observation alone, yeah, the probability of sunrise that Laplace gave would be our uncertainty based on the information that we already had, which was the frequency of sunrises that we have seen. And there was a comment yesterday, right, that we still, for example, the probability of sunrise is the number that we saw sunrises. And then something like this. And then there was a comment that, well, this is still a frequency, right? And that's right, because maybe what I should say is that so everyone, whether they are frequentist or Bayesian or not, they use both frequencies, which are facts. So this is frequency are something that we observe in real world, right? We only expect frequency to be equal to probability in the long run. So it's, in particular, infinite number of trials. So when I mean long, it's really long. It's something that we never attain. And everyone also use Bayes rule, even though they don't have to be Bayesian, because those are also Bayes rule is a mathematical statement, mathematical theorem. It's just how we interpret. For example, so here, yeah, for if we have so this case is not like a control random experiments, but we can sort of think of this as a frequency. But if I make a repeated trials of experiment that and count frequency, that would still be data from the experiment that we use to estimate or make model that will give further prediction. But that model doesn't have to be anything objective, right? It's just something in our mind that we use mathematical tool, theoretical tool to calculate probabilities and predict future events. The difference between Bayesian and frequentist would be the way that the meaning that they give to probability like this. Well, especially for frequentists, this wouldn't make sense because sunrise is not really, we don't have an ensemble of situation in which in some instances sun rises, in some instances sun doesn't rise. So for something objective, I would say is an agent it has to do with a person, someone, agent's uncertainty or I should say degree of belief. For example, probabilities would be something subjective. Or you could say this is also, you can think of this as based on ignorance of like the real state of the world, whatever that is. And I would say that fact never imply non-trivial probability. Right. So facts only imply trivial probability in the sense that if something happens and we say it happens with probability 1, and it never happened and it's probably zeros, but facts itself or properties of the world, something objective, well, at least in the classical sense, never really imply a probabilistic statement about our degree of belief, which come from ignorance, amount of information that an agent has access to. Well, for quantum mechanics, of course, you can decide for yourself and see for yourself whether you want to think of quantum probability as objective or subjective. Right. So maybe I will just write down what I said before. Everyone uses frequencies, and everyone can use Bayes rule. Frequentists would identify probabilities with long-run frequencies. Well, and by identify, I mean that they would think of that both of them are like actually the same thing. Although based on this discussion, I would argue that it's a categorical mistake to identify them because these are subjective and these are just facts, right? Although of course the sort of to identify the meaning of them are like the interpretation that they tag on, but of course if I just think of value, the value of probabilities and the value of long run frequency, they are the same because they are guaranteed by some kind of large number theorem, law of large numbers, which will be one of the things that we're going to talk about today. So any questions up to this point about today, about yesterday? Okay. So before before we get to laws of large number or concentration inequality, I should state some definitions first, just so that we are on the same page. So a random variable x is something that takes value little x in the sample space, right? With probability, so I would, because I'm lazy, I would use this abbreviation like yesterday, that this is with. Probability will be called P of the random variable x equals little x. But most people would not write it this way all the time because it's clear, it's too clear in fact, but it's too long also. So maybe they would write something like this, and just to emphasize that the random variable is distributed like that x is a random variable, and x is distributed according to some distributions, and so this is the way that people would write. For example, this thing can be for the normal distribution, and then in that case they would write like something like this, right? It's a family of distribution determined by two parameters, which are the mean and the standard deviation, or square root of variance. But when things are clear, we would just write this. So we have, when we have more than one random variable, there are notions that we can define, like joint distributions. Like this is, suppose that I have random variables x and y, right? And this logically means the same as the probability that both the value x, that the capital X takes the value x, and y takes the value little y, right? And if you want to write the probability of just one random variable taking some value, then you would have to do something called marginalize. So the marginal distribution, for example, for x would just be the joint distribution, and then you average over y, right? And this is clear, right? For example, I can write something like so if, say, I have events that x happen and then not x, and y and not y, the joint distribution would specify the 4 numerical values of these 4 events, right? And if I want to I want the probability of x being true, then I would have to sum over the probability in both cases, both when y happens and when y does not happen, and that's already exhausts all the possibilities for y, right? Yeah. And conditional probability, of course, we write it this way to means that the probability of x given that y has this value. And based on axiom 4 yesterday, so we define that this is the joint probability normalized by the probability that y is true, because this is the condition. And you can make sense of this in Venn diagram, of course. Also, right? If you have y and x, and you want the probability of x being true, given that y is true. So the condition that y is true means that you restrict yourself from the sample space to just this, right? And then you take the probability of this event, so x being true. But of course, so overall the sample space, the probability is normalized to 1. If you just restrict yourself to here, the probability is not going to normalize. So you have to divide by the probability of y. Especially pxy with y fixed is a probability, right? In other words, it sums to 1. Which you can derive from here, right? Because if I sum over x, then the joint will become the marginal of y, and so the numerator and denominator cancel. But pxy with x fixed is not a probability. And this is the way that statisticians use. So they would define the likelihood function. So if we go back to the discussion yesterday, right? So I say that something called likelihood is something like this. So now if I suppose that I have two random variables, that x is the source of the random variable for the data, and big data is for the parameter of the model. Right. If you recall, so in when we do statistical inference, we would like to, well, all that we see, all that we can gather are data, right? And we want to know the probability of the model being true. So we should consider the condition of probability in the opposite way, that we want P of data given X. But since that doesn't have any meaning for frequentists, so the way that frequentists do statistics, they would just look at this thing instead as a function of data, fixed X, and that is what they call the likelihood function. So this is a function of data given X. And this is not a probability. So maybe if you have something like this, and then they would say, oh, because this likelihood function is the highest at this parameter, then maybe it's likely for the model at this value of data to be true. And so that is the basis of the so-called maximum likelihood, a type of like maximum likelihood algorithm when you do this kind of inference. So they would estimate data. So people often denote an estimator by putting a hat on. They would say this is the argument that maximum, the argument that maximize this likelihood function. And two random variables are correlated. Well, maybe it's better to do it this way. So two random variables are independent if the choice probability is just a product, right? And then we can say that two random variables are correlated when they're not independent. Right? That means the probability of one value occurring for random variable x, for example, would depend also on what happens to y. But if they're independent, so for example, you can see, right, that if they're independent, this would just be the probability of x, right? Because then you use the axiom 4 again, then this is xy, and then divide by probability of y. But if x and y are independent, then these cancel again. And of course, we have Bayes' rule or Bayes' theorem, which follow immediately from the fourth axiom, which is the definition of, you can take it as a definition of the conditional probabilities. Because when I write something like this, so I can write the joy distribution as the product of a conditional probability with the probability array. But I can, so here I write it as the probability of x condition on y, but nothing stops me from writing it as in terms of probability of y condition on x, right? And so on two sides, I can write this equality, and then, well, depends on whatever direction that you want to write. Then I can calculate the conditional probability in one way from the conditional probability of, the opposite when I condition on the other variable. And the way that this is usually calculated, you would have your prior for y, so the probability, your belief that y is true, and then you have this likelihood function, or like conditional probability, and then so here would say that, okay, if this particular value of x happens, what is the probability that this particular value of y happens, right? So usually, sometimes when you calculate this, you would write this guy, the marginal, in terms of conditional probability also. That is p of x given y on the same side. By using this formula, which is kind of trivial, but they call it the law of total probability. Which is really just write x in terms of marginal, but then split it into conditional probability instead. P x y py. So if I put this here, I can rewrite the denominator, right? Y. So this would just be for one value of y. But here in the numerator, I sum over a dummy variable y prime. Something like this. And then I should also introduce the moments. Of a random variable. So the kth moment, mathematician would write it like this, and physicists would write it like this, and they would just be the sum of power of x, so power of numerical outcomes x, and then weighted by the probability of x. For example, when k equals 1, this is just the mean, well, it has many names, right? The mean, the average, the expectation value, which is the last one is a bit of a misnomer, but it's not really a value that you expect, right? Because, for example, I don't know, maybe in the past, the U.S. household has the average number of children in a family is like 3.5 or something, but you're not going to find a family that has 3.5 children. So and it is a fact that well, maybe if you want to be mathematically rigorous, you probably have to have some kind of condition to prevent pathological cases. But it is well, for physicists, what was the saying? So like if physicists think of like an infinite series or something, and maybe he doesn't know this converge or not, there's saying something like it's we assume it converges until proving guilty or something, until we can prove that it does not converge or something. So this is the same. What I'm gonna say is that, well, the situation that the random variable that we usually encounter, knowing all the moments is equivalent to knowing the distribution. And maybe this is not so easy to see. I think other way that people would do something like this is that they will use characteristic function instead, which is just like the Fourier transform of the distributions. And then you can, let's see, do I have some kind of argument? Well, not from the top of my head right now. And I also don't want to talk about characteristic function. But for some distribution, so let's say, yeah, let's talk about specific moment. The mean doesn't always exist for some distributions. So have you heard of an example? Or can you say, why would the mean not exist? And let's say we talk about continuous case. So in this case, it'd be something like this. So maybe like so when I said it does not exist mathematically, I equate it when this value is infinite also. I would say it does not exist. And you can sort of see it from here. So if the probability distributions fall off at infinity, slower or as slow as say 1 over x squared. So for example, if this is like 1 over x squared, you would have 1 over x here. And then when you integrate 1 over x, you get the logarithm of x, which, when you take the value of the limit, then it gives infinity. So for example, the usual example, which is a distribution that has many names, Cauchy distribution, Lorentz distributions, or non-relativistic Breit-Wigner, which is, well, this is just a cartoon. So suppose that I have, so everyone knows about Gaussian, right? So it's sort of, Gaussian is sort of like this, and it's never really decreased to zero. It just keeps going on. But at least it falls off fast enough. So for Breit-Wigner, you see something that's kind of more pointy here, but then it's fall off slower. In particular, so I open up Wikipedia. If it's centered at 0, it would be something like this. And gamma is just some parameter that sort of give like determine like the mass where it's fall off. But you can see that this is fall off as 1 over x squared. And so this one doesn't have an expectation value, for example. Oops. Okay. Oh, and I should talk about variance specifically because, well, we often hear about variance even though they're not moments, right? So if I define this quantity delta x to be the random variable x, and then subtract the mean, then the variance is this quantity square, and then you take the expectation value again. And something that you must have seen, and is an easy exercise if not, is that this is equal to this. So it's the second moment, and then you subtract the square of the first moment. And actually this has a name. It's actually the second cumulant, which is we're not going to define, but it's you define it by first defining the characteristic function, and then the logarithm of the characteristic function is the cumulant generating functions. So when you write it as a series, and the coefficient in that series are the cumulant. And sometimes it's nice, like you can prove the central limit theorem, that probability distribution of like sum of many independent and identically distributed random variables converge to like a Gaussian. That's the statement of the CLT, the central limit theorem, and is usually proved through the characteristic function, those kind of thing. And the Gaussian, what is special about the Gaussian? Because it turns out that the Gaussian is a unique distribution that has only the first cumulant and second cumulant, and then everything from the third cumulant vanishes. Those kind of things are not true for the moments. So all of the moments for Gaussians may not vanish, but it's still true. Actually, it turns out that all of the from third moments to like infinity, all of those are determined by just the first and the second moments for the Gaussian, just for the Gaussian. Yeah. Yeah, and when you do quantum information, sometimes example of things that kind of like this, kind of like Gaussian like this also appear, like the stabilizer states. I don't think many of you have heard of it, but Chem has heard of it. So like the stabilizer state, there are sort of states that are easy to represent, like efficiently representable, efficiently manipulable, and in a spatial basis, their wave function, their discrete wave function are Gaussian, for example. And some of you may have heard me talking about fermionic Gaussian states. Those are also Gaussian because all of the higher moments are determined by only the first and second moments, something like that. And if you have, well, and just to be sure, right? So if I have some distribution, so the mean would just be sort of the average where the most of the weights are, and then the variance would be sort of, it tell you sort of how they're spread out, right? But of course, when you want to think about some general statement about probability distribution, you shouldn't think of something like this, right? So a lot of people, I think, only think about something like this, like the unimodal distribution, where it just peak on like just one places. But of course, there's some some other distributions as well. And so for maybe something like this, it's harder to say that variance are the like some, yeah, there's still some kind of spread, but yeah, it's not like the width of the distribution. If you have say two variables, then you have covariance. Width is just this quantity which reduces to the variance when x and y are the same. Yes, and today we will calculate something like this for like independent trials of a random experiment. Okay, any questions so far? Oh, by the way, if I take the expectation value of this, I always get 0. Do you see it? Okay. Any questions so far? Because next we're gonna be working toward some kind of law of large number, which would justify an estimation of probability by frequency, or generally justify an empirical estimation of expectation value from sample means, for example. All right. Abbreviation LOL, which is not League of Legends. So the plan would okay, let's see. So first we will prove something called Markov inequality, which then leads to Chebyshev inequality, and then the special case of this applying to repeated trials would be the so-called weak law of large number. All of these are some kind of the same kind of concentration inequality. Inequality because it's take a form of inequality, which we'll see for a moment, but concentration means that usually when we want to estimate some statistical quantity by like taking like average of data, right? When we just take a few samples, or if the numbers are too few, then the value is sort of like all over the place. And we want to have some kind of guarantee that when we take more and more data, the estimator concentrates to the value that we actually want to estimate. And this is why these concentration inequalities are important. Okay, so for Markov, so this apply to, okay, and for all this inequality, there will be some kind of moments involved in the inequality, and I assume that all of the moments exist. If I'm a mathematician, I have to say every time that assume the mean exists, assume the variance exists. But in this case, the random variable x, we assume is a non-negative random variable, so it only takes value from 0 to infinity. then the statement is that we can bound the probability that x has value greater than some value from the value itself and the expectation value of x. I guess let's prove it on this side of the board because there's more space. Okay. So I think it's easy to start from just the definition of the expectation value of x. By the way, what do you guys prefer for the symbols for like the beginning and the end of proof? The end is QED, right? Yeah. So there's some symbol that's called there's a white square and black square in LaTeX, and I'm not sure if both of them are called Haumos tombstone or not, but they can be used to. So I use both, and I never remember which one I use for the beginning and or the end. Well, let's say just a proof. Okay. So I guess we can do general case which are continuous. So this would be the integral from 0 to infinity, right? Let me write. Which then I can split into the integral up to a, and then the integral from a, right? Well, and there we want the probability of x being equal to or greater than a, which is obviously this integral. And well, we also want this side, that side, to be greater than or equal in also. And so the easy way to proceed, right, would just be to ignore this term. And now the value of x in here goes from a to infinity, right? And so it's lower bound by a. And so I can say that this is always a, and then I pull a in front. Which is, yeah, the result that we want. So a general remark is that whenever you are presented with an inequality, you should always try to think about when the inequality is saturated, or whether the inequality is tight or not. So maybe just some vocabulary, because maybe you have some quantities that you want to bound, and then you have a bound in the form of an inequality, right? So maybe the bound is kind of here, and maybe the general case the value just goes to here. Then there is that in that case there would be a lot of gap, right? So the inequality is very loose. And maybe you want something that's more tight, which would be something that closer to the real value that can happen. And the remark that I said, I mean that, well, whenever you have an inequality, you should always try to figure out what is the instance that the equality is satisfied, and that we call saturating the inequality. So for example, yeah, can you tell me what kind of distribution make this make the Markov inequality becomes Markov equality? Any idea? Yeah. For example, right? Because okay, the simple way to proceed is just to see how many inequality we have, right? And then see what is the example where each of these become equality. And so our strategy was that we divide the space from at A. And so first of all, when I throw away this term, it would be an equality only if this does not contribute anything. So this means there's only some kind of distributions, non-zero distribution over here, or if you have a delta function at 0. Because at 0, the value of x is 0. So it's okay to have a delta function there. So one case, this is saturated by there's a delta function at 0. So here, delta x. And for this case, this will be an equality only if if the value of x that we pull out greater than a does not contribute to the final integral, right? Which is the example that Dunk gave, which is if you have a delta function here. Yeah. And so just to summarize, so Markov inequality is saturated that when the x is either this or it peaks at A, right? All right. Now we move on to the Chebyshev inequality, which is closer. It's going to be closer than what we want, which is to bound the which is to bound how far the mean value of some random variable is close to. Well, let's okay. Let's see what is the actual statement of it. Chebyshev inequality, and then this said that we are bounding the difference between the random variables, the value that we got from the random variable and its mean. And then maybe I want well, I can put either side here, right? If we are really giving if I put it like this, where epsilon is some positive number, but it can be anything, can be arbitrarily close to 0. If I put it like this, then which means that I'm bounding the probability that the value of x is far away from the mean. which is something that we don't want, right? So it's like a bad event. Then we want to suppress this probability, right? And I think let me check. I think it's just the variance. Oops, that's square. Okay, so how do we prove this from the Markov inequality? So the inequality inside the probabilities are two-sided, right? Because it has absolute value. So it's actually two inequality that this value is greater than this if it's a positive number, or if it's negative, then it's less than minus epsilon. Right? Okay. But of course, we don't want to deal with it, and the easiest way is just to square the whole thing. So we consider instead this. Right. And the probability of this event being true has to be the same with that, right? Does it make sense? Okay. But now here we can apply Markov inequality directly, right? Because it's already informed here. So we replace the random variable x here by this kind of thing. I don't know what people call it, but I call it a deviation. Right? Oh, sorry. Oh, yeah, sorry, correct. Yeah, that's why there's epsilon square in the theorem. So so you would have yeah, it's very direct because this is already the variance, right? And then this is epsilon square. So now we're gonna apply this statement, this concentration inequality to when. So this is from observing the value of random variable x just one time, right? But now we want to consider repeated trials. And so we have a set or collection of IID random variables, so x1, x2, x maybe k, where IID here is the sort of common assumption in theory that these all random variables are, first of all, independent. And so they're all uncorrelated in a sense, like if I say if I want to do repeated random tries of like a coin toss, this just means that different coin toss, like first coin toss, second coin toss, has no correlation. So whatever the result that I have obtained before doesn't affect my future coin tosses. And the other one just means identically distributed. Which means all of the x for any k is distributed according to some probability, some distribution.
Why? Why to square? Why we're not playing in first
Why do we?
Why we not playing? based on the equal than absolute x. The absolute of the deviation over epsilon y equal to in this case.
Sorry, so you're saying that why don't apply like Markov directly? Okay. Yeah. อันนี้มันสั้นลงเรื่อยๆนะ
ก็คือทำไมไม่เขียนว่าในตรงนี้มันก็เป็น
Right. So the question is, why is this not true? Well, because in the Markov inequality here, so I have, say, I have some distribution, right? And then I have the value of A here, and I only consider one side of the distribution. So I only consider the total probability mass that is greater than A here. But here, if so x could be the real value x, could be greater or lesser than here. And so what we doing, right? So like maybe this is the real the underlying distribution which has the mean here, but the value can be here or here, and we are bounding just so the epsilon here are from either side. Yeah, so we're really just considering we are considering this. We are two-sided, so this does not apply directly. Yeah, but
we think of the absolute value as a new. So let's say so it's already clicked to only once. If we think the whole thing as a new random.
Oh God.
This is still true, but I think it's not useful because we can bring that to the absolute.
Yeah, well, but oh God, this cannot be true, right? Because or is it? Let's see. Oh, right. So if I take absolute value before, yeah, I guess you can do that before taking the expectation value, and so this would not be necessarily 0, but it's something else. No, I mean what? Yeah, what Dang said was that because I take absolute value before this, it may not be 0. Yeah, but yeah, you will get something. Yeah, I don't know if it's useful or not. Yeah, thanks for the question. ไม่ซีโร่ฮะอะไรนะมัน
ไม่สนใจ
ไม่ถ้ามันไม่มีเนี่ยมันเป็นศูนย์มันคืออะไรก็ไม่รู้ Yeah, so it's still a valid. You would get a valid inequality. It's just something, I guess, it looks more complicated. I'm not sure if it's useful or not. Yeah, but yeah, good observation from all. Okay, right. So now we just introduce this, and here I'm not yet specify which distribution this is. The law of large number apply to any distributions. But after this, we are gonna, once we get the law of large number, I will think about the frequency, which is in the sense, so more than that, I would think about a random variable with finite sample space. So like throwing a die or throwing a coin. But here is arbitrary, so the law of large number in general doesn't care what this is. Oh, conveniently, yeah. So then I define the sample mean or empirical mean empirical which is for n trial in total, take the average of the value that you get from each trial of the random experiment, right? So different xk, these are some numerical values of the random variable here. Yeah, somehow now I write all of them as capital letters, but and then we want to see if this how close or yeah, this value is from the actual mean of the underlying distributions. Yeah, so maybe here I have to say that this is whatever that x is also distributed according to the same distribution of all the x. And this is sometimes so this is sometimes called theoretical mean to contrast it to empirical mean. Right? And you understand like the meaning of that this suggests, right? Because empirical or sample is something you gather from like taking a random sample or from gather data from population. So this is the actual data value measurements that you get from experiment or whatever, and then this is the thing that you calculate on paper, right? Just because you assume that the distribution, underlying distribution, is known, but of course you the actual the thing that you can get from the real world, the only thing are sample mean. And so you want to know if I gather more and more data from an identical distributions and then sum them over and then average them, whether it's going to be close to the theoretical mean or not. And we can sort of see already that this has a very similar form for this. We just have to calculate the variance of this guy. Oh, maybe first thing that I should say is that the mean of the sample mean is the same as this. And this it's easy exercise. But for the moment, you have cross term. So we are gonna calculate it now. So I have sum now with two indices, right? Okay, so let's for convenience, let me just compute this alone. Well, oh sorry, it has to be delta right? Let's see. Right, it has to be delta. Right. Yes. Sorry, what was the question? Can we? Yeah. So here, x doesn't have to be non-negative. It's kind of different, I would say. I mean, the assumption is more general, but from if you just look at the statements, there are different statements, right? Yeah. Is that okay? Okay. Sorry. So now I have to calculate this. So I have to square this guy. Oh, right. Right, so that this just directly comes from here. Oh, sorry, because because what we want to calculate is actually the variance, right? Okay, sorry. The variance of this guy by definition, right? So this would be yeah, and this is how we can get the deviation random variables in the cross terms. So so for okay, now I have the n square yeah, that have the sum with x l x okay right, and then now if I just look at this, yeah, and please don't hesitate to let me know if I make some error. So here I can just write out so x. So if I just write out this would be let's see. Let me write this out first. xk. Oh God. Then expectation. Does it look right? So if I have to so maybe let's just do from the beginning, right? If I want to so delta s would be this guy and then I subtract the mean, right? Yeah, which would just be this, right? And now I square it. Okay. This is n square. Okay, and the sum does not include this guy. Oh God. Is it easier to write it like this? Yeah, and then where yeah, no. From this I will get double indices, and then okay, and then now I have to take expectation value of the whole thing again, right? Because this is xk minus x. Sorry. So what I wrote before was already correct, and it's just that in the notes I try to calculate this, which I already erased. I try to calculate this first, which will get one of the term in here. So if I so the variance of S, I would have this and this, right? And so this term is easy, but then this is from that. Okay. Sorry. So let me redo everything here. Now we know. Okay, I want this first. And that's why there's this weird thing here, because here I just add and subtract the expectation value of x. By the way, this is all in my statistical mechanics note on probability, which I posted on the website this morning. So so it contains more things than I'm talking about here. For example, the like cumulant and proof of the central limit theorem. But here, so if you just multiply them all and use the fact that that expectation value of expectation value is still the same thing, then I will have something like this. And then the correlation, the covariance term. But then we know that this is always 0 for the deviation of the average value of the deviation random variable for just one of them. But then here, what is this one? Well, it's a kind of covariance, but we already assume that if K and L are different, then they're independent, right? And so I still have the first term, and yeah, this turns out to be this because I think this is a covariant. And I believe it can be written in a similar way as like the variance of just one variable, which is xk minus the product. So if xk and xl are independent, then these two are the same, and the covariant is 0. So what is left is just the diagonal term, and so I have the Kronecker delta here, and then it's just the variance. Is that okay?
we just use this to calculate say if they are
This is the same thing, right? Whether you whether I calculate the covariance or this guy. And so now if I say, okay, well, what is the, not the variance, but just the expectation value of the square of this thing? So just putting each term back in the sum. Right, then I will have this because at this, when I put this in the sum, then the Kronecker delta collapse the sum to just one value. And then this is the variance of x. And so all in all together, then the variance of the sample mean is it's just this thing minus this thing. Well, what is this? Then this is just the mean square, which is the same as the mean of x square, right? So this is the term that got canceled, and so I get this x over n. And so all in all, we get an inequality that says that, or maybe we can just point to there. You have that the probability that the sample mean is close to the theoretical mean, and I need to erase something here. Oh, sorry. If I want to use the same version as that, then I have to do this. Right? Then this is the variant of the random variable x over n times epsilon square. Usually the LOL is the statement of is about the limit of this probability in the limit n going to infinity. Well, 0. If it has a finite mean, finite variance. But even though this is the form that people usually call the LOL, is important to, I mean, this factor gives us information, right, about the rate that this goes to 0. So it's important. In fact, it's a lot of time it is crucial, especially in quantum information science, that we know or we can calculate the rate of convergence, because all the data that we gather in the real world are finite, and so we're never gonna attain this limit. The question is how fast this limit is attained. Sometimes if okay, maybe I can talk about some specific warning related to the central limit theorem. But first of all, so let's say this is remark 1. Remark 2, well, what is the strong LOL? Because people saying this is a weak LOL. Well, is this just a different kind of convergence? Sometimes people say, mathematicians call this convergence in probability. So for this, you would just, the statement is, the difference is that the limit is now in here. This probability of the limit. So it would be a statement about this instead, but then the other side of the probability is still 0. Although, well, this one is not directly obtainable from that, right? Because this one, going from here to here, I just take the limit of both sides of equations. But here the statement is a little bit different, and actually it sort of have a different mathematical interpretation, in the sense that now we are saying that there is like a really big, like infinite space of limiting sequence. Okay? And for each sequence that Sn limits to in this like really large space, some of them really limit to have this value, and some of them don't. And so you have to put like a probability measure on that like really big space of infinite sequence. And it's kind of different, but it's called strong because it turns out this statement implies that statement, but not the other way around. A related statement is the central limit theorem. So note that both of these does not say that the distribution of well, what distribution I want to so suppose that I think about frequency, right? So maybe I have an experiment with a finite number of outcome, and then I just look at outcome k, and so I count the frequency by just counting the number of occurrence of outcome k, and then divide by the whole thing. And then you can apply this kind of statement, and it would say that the mean of the frequency will be close to the mean in the theoretical sense. But it does not say that the distribution of this will become the same as distribution of x. For those kind of things, you need a statement like the central limit theorem, which say that if you have a sum of large number of IID random variables, then they converge to Gaussian. However, it turns out that the CLT is, well, I don't know like a theorem or a rigorous statement of this, but it somehow is known that this is really bad for tails behavior. So it's the distribution. So right. So if I have like okay. Distribution of a sum of random variables, IID random variable, that's maybe like have to normalize in some way. By the CLT, this will converge to the Gaussian in the limit of n going to infinity. However, for finite n, is usually Gaussian is a good approximation only near the mean, but not the edge. Yeah, and sometimes tails behavior kind of go wild. And this is the sort of example that I want to bring up when I talk about this first statement, that if the if the bad behavior, if the bad events that we don't want fall off exponentially as the number of n grows, then we tend to think of it as like as good as deterministic, right? That we basically almost have a deterministic protocol that we always have like good events or something. But if the probability of bad events that we don't want fall off like logarithmically, any realistic number of n is not going to make this bad event goes away, for example. And so it's really important when we devise some protocols, some like probabilistic protocols in quantum information, that we really need to bound to know how errors is suppressed with respect to like the number of tries that we perform that protocol or whatever. I think the time is running out. So any question for today? The tails. So let's say that this is a Gaussian, and so it's like a limiting distribution that we want our long run sum of the distribution to look like. But in reality, if the number of n of the random variables are just moderate and not like really large, like close to infinity, the distribution that you have from the CLT, it will sort of mimic the Gaussian well close to the mean, but it sort of do something really bad over here. So it will not look like Gaussian far from the mean. Yeah, and so this is where the deviation from the mean value is large, and so mathematician has something called the large deviation theory that deals with this. And tails events are important, right, in the real world, like the financially catastrophic events that happens like once in 100 years. These are low probability events, or like world-ending event like aliens invading Earth. These are very low probability events, but when it happens, it have a really big effect. And so people in finance like think about this all the time. This tail event. Yes, so I think next time, unfortunately, we cannot finish the talking about probability today, but the homework problem, the first two problem on probability, you just need to know like basic definition, like conditional probability based theorem, and you'll be fine. So next time, let's see. I have to decide whether it's worth our time or not. So just one more thing that I want to talk about probability is that how you justify the probability axioms from the subjective point of view. And I think I can talk about it pretty quickly, but I don't know if it's understandable or not. But let's try it tomorrow. Yeah, before we go on to talk about entropy. Yeah. So thank you for listening and for asking questions and answering questions. Yeah. See you tomorrow.